Okay, everybody, welcome to Chem 1331. If this is Fundamentals of Chemistry 1, if that's not the class you're signed up for, you can stay anyway, it's cool. We'll have a good time here, so you might want to. All right, so this is going to be your favorite class this semester, I hope. I promise, maybe. But we're going to get into first today talking a little bit about the syllabus. So we're not going to have a syllabus day as it is. We're going to have maybe a syllabus half day today to go over some important things about the course, and then I will jump right into the Chapter 1 material. Now, if you've seen the emails that I sent through Blackboard, there's also a review chapter in our textbook that we expect you to be responsible for. This is stuff that you have likely already seen before in high school or other classes. It's stuff about units and unit prefixes and unit conversions and a little bit about density. So all that stuff we kind of expect you to know, but there are some resources in Blackboard now to help you review that if you need to. There's also a homework assignment that I think now just opened up. It's for the review chapter. It doesn't count towards anything. It's just for your sort of self-assessment to make sure that you know that stuff. So I encourage you to take a look at all of that, especially this first week, since the first homework assignment is not due until about 2 weeks from now, so you have plenty of time to do that one before then. So if you haven't got my emails through Blackboard, make sure that you have access to the Blackboard. You should, as long as you're registered for the class, and also make sure that you're checking the email address that's associated with your Blackboard account, because that will be the primary way that I will communicate with all of you throughout this semester. Okay? All right, so let's get into it then with some stuff about the syllabus. So the textbook is Zoomdale and Zoomdale's Atom First approach. There's been some questions, and there's questions every semester about if you need the OWL version to access code. You don't need anything like that. You just need the book. Even the book is not maybe 100% required, although I do highly recommend it. So you don't need any sort of access code. If you got the access code, there might be some stuff in there that you can use, but it's not going to be required for any of the assignments. I'm not going to really refer to that resource at all directly. But the textbook is something that I do encourage you to have and to use as one of the many resources you'll need for this course. Another thing that's good to get out of the way is the calculator requirements for this course. You can only use a non-programmable calculator. Most people use scientific calculators, like the TI-30 series is a very popular one. There's many varieties of those that work well. But you're going to be required to use those on the exam, so you might as well make sure you have it and make sure you know how to use it, because you don't want to be fumbling around in an exam problem because you're not familiar with the syntax of the calculator you have with you. So I encourage you to get that addressed right away. If you don't have a legal calculator for this class, get it before the first exam so you can make sure you practice with it. All right, so the grading in this course, you guys have likely heard horror stories about how harsh the grading is, and so here it is for you to look at with your own eyes, and I'll explain it to you quickly. So it's actually a pretty simple system where basically each exam question counts as 1% of your grade. So we're going to have 3 midterm exams that are going to be 20 points each, 20 questions, so one point per question. Is always going to be the case on the exams. So those will add up to 60 points, or 60% of your final grade. The final exam is a bit larger, so it's going to count for 34% of your final grade, so it's worth about 1.8 times a midterm exam, and it's also 34 questions then, so again, the length of the exam correlates with how many points it is. And then the homework is the one thing where it's not 1 point per question, it's something like 0.01 points per question, which is a lot of homework questions, and they will add up to eventually at the end of the course 6% of your grade, or 6 points out of the 100 that we give you for this course. So I'll explain a little bit more about how the homework grade is calculated in a bit, but that's going to be something that is a measurable but not huge part of your grade. And then there will also be 2 bonus points available to you. I think in a previous version of the notes I said that these were determined from in-class quizzes. We don't have in-class quizzes anymore. We're trying something else out the last couple semesters, but there are still 2 bonus points available, which would be, again, up to 2% of your final grade, not any more than that. And I'll explain those in a second as well, how we determine those. All right, the grading scale is here. It's a little bit more lenient than the standard UH scale. So I think the standard UH scale has an A at 93, and we have it at 90, and A minus goes down to 85, and so on. So you'll see here that it's, it's sort of divided up in this way. You'll also notice, especially as you get towards sort of the middle of the grading scale, the B to C minus range as it is, most of the grades are only separated by about 3 percentage points on the scale. So that's where those 2 bonus points can be very significant for you, because in many cases those 2 points are going to be the difference between one grade and another on your final grade. So maybe 2% doesn't sound like a lot, but if you take a look at our grading scale, it certainly can make a difference in many cases. All right, so that's a little bit about the grading scale. I encourage you to read the syllabus more on your own, and if you have any questions, please let me know. I'm happy to address those anytime. All right, some more details about the homework assignments. So this first part of the notes is just going to be a wall of text so that you guys can have all this information when you're on your own, so you don't have to necessarily worry about writing anything down just yet. We'll get to that when we start actually teaching you chemistry. But anyway, about the homework. So all the homework assignments are done on Blackboard. So again, it is critical that you gain access to Blackboard and know how to find everything for the course, because all the assignments, homework and exams will be there. And they're typically going to cover material from the past 1 to 2 weeks of class. So we're going to cover 9 chapters in our textbook. There's going to be 13 homework assignments. I think I guess this didn't update. There should be a 13. Sorry, we've oscillated between 12 and 13 depending on the semester. But anyway, there's basically 1 per week and a little bit more than 1 per chapter. So most chapters have 1 homework assignment. Some of the chapters will have 2 homework assignments associated with them. And they're going to cover stuff from roughly the last 1 to 2 weeks. And we'll try to get ahead of the homework a little bit. So again, so you're not doing assignments on things that you're currently learning or haven't learned yet, obviously. And we do drop your 2 lowest homework scores. So that's going to be something that'll factor in your final grade at the end. And as I said, it counts for 6% of your grade. Each homework assignment is 12 questions, and the scope of the questions is very similar to the exam questions, not obviously identical, but they're going to be of similar length and difficulty. So if you can get really good at doing the homework questions, you can feel like you're confident in your preparation for the exam. And then each week we give you 4 attempts maximum on the homework assignment. So, and we only count your highest. So I should say that only the highest one is going to be counted towards whatever your homework grade is. So there is no detriment to you to do all 4 attempts, and I'm going to harp on this over and over again throughout the semester, that this is something that all of you should do, is do all 4 attempts of the homework assignment every single week. Typically, in a typical semester, the average student does 2 homework attempts per week. So they're basically wasting 2. Last year we implemented the bonus point system that rewards you for homework attempts, and that went from 2 to 3 attempts per week. So still on average, everybody's throwing away a whole attempt per week and a chance to practice. And like I said, it won't hurt your grade to ever do more attempts because we only count the highest attempt anyway. So that's something to keep in mind. And then each attempt, I believe, is 48 minutes. I don't think they've changed that, but it's similar. 4 minutes per question, so not too different than what you'll have on the exams. Here's the part to keep in mind about the sort of the window for doing each assignment. So each new assignment will open up Sunday at 12 a.m. and then it will be due the following Sunday at 11:59 p.m. So basically you have an entire week to do each assignment. Now here's the part that throws some people, especially at the beginning of the semester. So if you're one of the large percentage of people that waits until the last day to do your homework assignment, don't be that guy, but some of you will. Then what's going to happen is when you log into Blackboard on Sunday, there's going to be 2 homework assignments available. There's going to be the one that's due that night and the one that just opened up. And you need to make sure you do the correct one. And that's especially confusing because in Chapter 2, there are 2 assignments, A and B. And every semester I have probably about 50 students that do the wrong Chapter 2 assignment on Sunday because 2 of them are open and they do the wrong one. And I'm warning you now so that doesn't happen, but I'm sure it still will for some of you. But anyway, just be careful. We have in Blackboard, a table that shows all the homework assignments, when they're due. So just make sure if you're trying to do that homework assignment on the very last day that it's open, if you wait that long to do some of your attempts, just make sure you're doing the correct one, because once it's due, it closes. You can't go back and do it again. So just pay close attention to that, and it's not a big deal. It'll be fine. The other thing we do and I thought I updated these notes, but I guess they didn't save properly. So there's actually 4 more attempts. So the other thing that we do is after each homework assignment closes, we open up the same exact set of questions. It's a question bank that you're going to randomly draw from for all these assignments. And we open it up as practice homework. And that allows you to go back in for no points, no credit or anything, but it allows you to go back and revisit some of those questions. So you can go, and people a lot of times use this, especially as they're preparing for exams, to basically review some of the old homework questions that they haven't seen in a while. And you can have up to 4 attempts on the practice homework, which don't count for anything, but are another great way to practice. So basically, for each week of the course, for 13 assignments that we have, you're going to have the ability to do 96 practice problems between the 48 for the 4 regular attempts plus 48 more for practice attempts, which I encourage you to save some of those for later, for when you're preparing for exams and things. But in total, for each assignment, you have the ability to practice 96 questions. That's a lot. If you can do all 96 of those questions without any resources, and then you can feel pretty confident about your exam preparation. All right. And then speaking of exams, everybody's favorite part of the course. So they are taking in everyone's favorite Soviet office, CASA. So they're going to be there. So we're not going to have any exams in class, and I won't be there for the exams. They're going to be proctored by the CASA staff. And you'll get more information about this in the near future if you haven't used CASA before. It's delightful, and you can sign up in advance for the time that you take the exam. So each exam will be open for 3 days for the midterms, Monday through Wednesday, and a little bit longer for the final. You sign up for a time about 2 weeks in advance is when it opens, and then you go there at that time and take the exam whenever fits your schedule. So each midterm question, as I said, each midterm exam, as I said, is 20 questions, and you'll have a 75-minute time limit. So that's close to 4 minutes per question, a little bit faster than the homework, but similar pace to the homework assignments. And then the final exam is a little bit faster paced, although we tend to give you questions that are a little bit more straightforward and less time consuming on the final, and that's going to be 34 questions and a 100-minute time limit. And the final exam is comprehensive. It includes everything. So because we're in Blackboard, there's a limitation on the types of questions we can ask you. We can't ask you to draw complicated diagrams or write essays or anything like that. So you're going to be limited to mainly multiple choice. Probably close to half of the questions are multiple choice. And then there's going to be some where you have to type in a short answer, either maybe 1 or 2 word answer, or number is very common where we're doing numerical questions. So those are the types of questions you'll have on the exams. And as I said, they're very similar in style to the homework questions. So again, that's another incentive for doing a lot of homework attempts, is to get really used to the types of questions that we ask and how we, and get comfortable with those. I already mentioned scientific calculators are allowed. That's that and a writing utensil is all you can really bring with you. And then we will provide you with a periodic table and a list of constants. So CASA will have it, I believe, sort of posted right by the computer for you to look at. And then you can also, I think they should also give you scrap paper, plenty of scrap paper to do work on, but we don't grade or collect any of that, so that's just for you to use as you're taking the exam. The periodic table that we use is already posted in Blackboard, so if you want to get accustomed to what it looks like and what's on there, you can always download and look at it. And that's one that I'll use in class too when we start using the periodic table more often for things. All right, so my goal, and barring a weather disaster that cancels class or anything, we should be able to maintain this, is to finish all exam material at least 1 to 2 weeks in advance. So that way you're not going to be tested on material that you just saw or currently in the process of learning. So just like for the homework assignments, I'll try to get a little bit ahead of the exams so that by the time we're taking the first exam, which is chapters 1, 2, and 3, we've already moved on into chapter 4, so you'll have all that material already sort of in the bank for you. So that's going to be the timing of everything. And then when you take the exam in CASA, you're going to do it in Blackboard also. So you're going to use the same Blackboard portal that you do all your homework assignments on. The only difference is we use a restricted browser to make sure you're not surfing other websites while you're taking the exam and all that, but it's going to look exactly the same as what you do at home on Blackboard. And then once you submit the exam, you will get your score right away, so you'll know. Some people close their eyes and don't look because they don't want to know, but if you don't, if you keep your eyes open, you'll see what score you got in the exam, and you'll know walking out of CASA how you did. That said, you won't be able to actually see the questions you got right and got wrong until after everyone finishes the exam. So as I said, for midterm exams, they all close Wednesday evening, so Wednesday evening would be the time that everybody can log into Blackboard and take a look at which questions you got right, which questions you got wrong, to sort of help you understand how your score was determined. And then if you think that there's cause for a regrade, so if you think that one of the questions was graded incorrectly, or there was a second interpretation of it that you had that was not accounted for in the correct answer, you're always welcome to ask me to take a look at it. Those need to be done within 1 week, though, of the exam closing. So I will give you reminders about that when the exams happen. But just to make sure I'm not going back at the end of the semester and regrading 545 exams from you guys, we make sure we close that off after 1 week. It's pretty rare that a regrade results in a higher grade being given. These questions are reused over and over again. They're vetted by me and by other people, so it's pretty rare that there's a problem. Now, occasionally Blackboard has some technical glitches, so you have to, if something like that happens, you'll have to inform the exam staff. We'll get all this stuff later on, though, as we prepare for the first exams. But anyway, there is a possibility for regrade, but it's not something that helps most people because typically the exams are graded correctly. All right, so here's the information about the bonus points that I'll be offering. So basically, this is the one part of the class that I actually have control over how I grade. So we are, this class is what's called a departmental class, which means that we want all the sections to be the same in terms of how they're graded and, the material that we cover and all that stuff for the whole department. So there's like 5 sections this semester, all of them covering the exact same stuff at the exact same time. The one thing that the instructor has free reign over is how to give out the bonus points, up to 2%, as I said, is what we're allowed. So what I've tried to do, I've tried a few different things throughout the years. What I tried last year, which was, and I'm going to continue it again this year, is to have the bonus points be tied to the number of successful homework attempts you complete. So as I said, you get up to 4 homework attempts per week, and it is in your best interest to do all 4 of those. And to further incentivize you to do that, this is how you're going to earn your 2 bonus points. So basically, what you will do is you're going to do your homework attempts, and Blackboard keeps track of how many you do, so I'll be able to track that. And for each attempt that you complete where you get a score of 5 out of 12 or greater, it's very rare for somebody to actually try on a homework assignment and not get 5 out of 12. So basically means as long as you try, you're going to probably get that score or higher. This is just to prevent you from opening the homework assignment, checking social media for 48 minutes and submitting a 0 and thinking that you're going to get your bonus points that way. That's not really the point of this. So the point of this is we want you to actually put effort into all 4 of your attempts, which is why we have a score threshold of 5 over 12 to count it as a successful attempt. So it's not typical to get that, and very few people, as I said, will actually put a lot of effort into an attempt and get less than 5 out of 12. But you do need to register that for us to know that you are actually putting effort into it. So for each attempt you get, that's 5 out of 12, you're going to get half a bonus point for that week. So that means you get up to 2 bonus points for your weekly bonus score. And remember, that's going to be then average at the end of the semester. So it's not that you get 2 points per week, it's that you get 2 points each week. And then at the end of the semester, we average your weekly bonus scores to get a number out of 2. That's going to be the number that we add to your final grade. So it's going to be no more than 2 at the end of the semester, but it's a culmination of the whole semester. And just like I do for the homework grades, I will drop your 2 lowest bonus scores. So if you have a week here or there where you're not feeling well, you're bogged down with something else or whatever else comes up and you can't do all 4 attempts, that's okay. We'll drop your 2 lowest ones and you can still get the full 2% bonus even if you miss a couple weeks for whatever reason. But like I said, we're going to use those homework attempts that you do as a way of calculating up to 2% bonus. So don't think it's ever going to be higher than that. There's always some confusion about how you calculate this, but it's basically just averaging all of your weekly bonus grades, dropping the 2 lowest throughout the semester. All right, so that's how we're going to calculate the bonus points. And the reason we do this is because we're trying to encourage you to do more attempts on the homework. Now, what I will say in sort of full transparency, and I'll get here in a little bit to sort of typical grade distribution in this course. So last year when I taught this course, exactly 1 year ago, spring 2019, was the first time I used this system for doing the bonus points. And it was reasonably successful. So as I said, we went from about 2 attempts per student up to 3. Now, that said, the final grades didn't really improve at all, so whether it was effective or not, I guess, is up in the air. But at the same time, it did encourage more effort on the homework. Now what we need to work towards is making sure that we're actually learning from those homework assignments and not just doing them. So that's going to be our goal for this semester. Let me get my pointer real quick so you guys can see what I'm pointing at when I do. All right, there we go. All right, so like I said, that's how we're going to calculate the bonus points, 2% maximum. All right, and then finally, before I get into some things about how to earn a good grade in this course, some advice at the beginning, some information about me. So as I said, all these sections of Chem 1331 are largely coordinated. The big difference is who stands in front of you to teach. And so In this section, I will be the instructor, obviously. That's why I'm here talking to you guys. And my office is in Circ 5023. All right, so that's pretty easy to find. So we're about right here right now, in that corner of the Science and Engineering Research Center. And then if you just walk under the covered walkway, the building that everybody cuts through to get to the other side is the building that I'm in here. And then you just take the elevators up to the 5th floor. Or if you can find the staircase, if you're a good explorer and can actually find where they are, you can take the stairs up too. They're not easy to find. But the elevators are right there, and they're only broken about half the time, so you can get up there pretty easily. All right, so my office is on the 5th floor, the top floor of that building, 5023. Now, in terms of office hours, so I've done different things in this course, and typically I don't get a lot of students, as this picture shows, I don't get a lot of students visiting my office during office hours for whatever reason. So I will have some that are regularly scheduled. So as I'm showing here, they're going to be right before class. It seems like that was a pretty popular time for students to drop by if they don't have another class before they come. So that's going to be 2:45 to 3:45 Monday to Wednesday. So basically the hour before this class starts, with a little bit of gap time for me to get over here. And so that's the time. Now you don't have to come during that time if you can't, but that's basically where I will more or less guarantee that I'll be in my office. I'll try not to schedule other things on top of that, and if you come that time, I'll be there and ready to answer any questions you have. The other way you can come to my office is the office hours are, as I say here, by chance. So that basically means you're always welcome to stop by, and if I'm there and I'm not doing anything else, I'll talk to you, no problem. Now that's, of course, I say by chance because I'm not always there and I'm not always not busy. Believe it or not, I have things I have to do once in a while. This is a real job, believe it or not. So the by chance part of it, if you want some idea, typically I'm on campus and between about 9 a.m. and 5 p.m. at least. But if you come during those times, I may or may not be there, but there's a good chance I will be. At least half the time I'm probably in my office. But the other good way to do it, if you don't want to worry about not being able to find me and you can't come to the regular office hours, is you can always schedule an appointment. So just send me an email of when you're available to meet, and I'll see if any of those times work for me. And I'm happy to set something up with you, and that way you'll know when you come there that I'll be there and ready to meet. So there's a variety of ways to do this. I want to make myself as available as possible. So, I encourage you to come see me. I know there's maybe a little bit of a psychological barrier when there's 545 students of thinking like, oh, his office hours are going to be jam-packed and never going to have time, but that's not usually true. It's a little bit true before the exams, but in a regular week, my office is pretty empty most of the time, and you're welcome to come by and sort of make those regular visits to make sure you're staying up on the material. All right. And the best way to contact me is by email. If I'm in my office, I'll probably answer my phone, but email is the best way, and I'll try to be fast about that. All right, and then another resource that I want to point you out to is the YouTube channel that I run for this course. So this little recording bar up here on the right is recording what I'm doing now. It's a screen capture and audio capture as well. So every lecture is going to be recorded, and they're going to be posted in the evening after class. So that's sort of a way for you to go back to old lecture material that you may not have followed the first time around, or in the hopefully rare cases that you have to miss class, you can sort of get caught up on it. There's some other things that I will post to there as well on a regular basis. So starting after the first homework is due, so that's not until 2 weeks from today, but every time a homework assignment is due, the following Monday, the day after it's due, I will go through the homework results, find out the questions that you guys had the most trouble with, and I'll do probably roughly 8 to 10 of those problems. I'll work them out and sort of maybe explain some things that were common misconceptions or things that I might not have covered in the lectures as much detail as I should have or could have. And so those homework reviews will be posted first half of the day Monday. I encourage you to send me requests for those. If there's a certain collection of homework questions you had specific trouble with and want me to cover them in the review, that's fine. Those are not those homework review sessions are not live. It's just me in my office by myself. So there's not like a session associated with those, but the video will be available for anyone to watch. The exam reviews are the other thing that will be on YouTube, so I'll have more details about these when the exams come closer, but typically every Friday afternoon before the exam starts, as I said, every exam for the midterm starts on a Monday, so the Friday before that, I will have an exam review session where we'll go through a set of questions that sort of simulates the actual exam. I'll post those in advance so you can work them out on your own beforehand, and then those exam review sessions probably will be in this room if it's open. They're not usually that full, but we just usually take this room because we're here anyway for our regular classes. And so you can come live if you want to and are available, and then the video will be posted as well after that on Friday evening, so you'll have the weekend to check that out. All right, but one thing I want to emphasize is that there's a temptation of since I record all of the lectures for. And especially now that I don't give you bonus points for anything that relates to your in-class participation, there's a temptation for you guys to just not come to class and think, oh, I'll just watch it on YouTube. But think about how you typically watch a YouTube video at home and ask yourself, is that conducive to actually learning? Considering the multitasking that you like to do and the many devices that you have in front of you. So the point is that it was the same way when I was in college. So I'm not trying to belittle you guys at all. I was exactly the same as this. Very few people have the discipline to sit down on their own and watch an hour and 20-minute video and really absorb it in the same way. So I do think that coming to class is still a critical component of this course. It's a way of you keeping on task, getting a regular introduction to what we're doing, and sort of staying on track with everything that's happening in here. And I encourage you, especially the lecture videos in YouTube, to mainly use those, as I said, to rewatch things that weren't clear to you in the lecture the first time, or in the rare cases you have to miss a lecture for some reason. But I don't intend these to be a substitute for attending class, and I have data from previous semesters, even when the YouTube videos were available, that people that actually come to class still do better in the course. It's not, that's certainly still true. All right, so it can't be the only resource you use, and it can't be a substitute for attending class, and I want to make sure I emphasize that. So some more about how to succeed in this class then, and so here's some statistics related to that. So this is from spring 2018, 2 years ago. Last year didn't look too much different, or if anything, a little bit worse. But basically, as you guys probably know, this is a hard class, and I am aware of the challenges that are in place in terms of how we grade the course. I'm not oblivious to that. But I want to say that, if you look at the average, it's a C or usually a low C is sort of the typical average grade in this course. This grade distribution is only for people that actually finish, not counting the students, usually about 15 to 20% that drop before to take a W. In total, if you look at the percent of students that get D's, F's, and W's, that's what we call the DFW right here that we keep track of. That's for my sections anyway, has been about 44% historically. So these are not numbers I'm proud of, and these are not numbers that I'm trying to say to scare you, but obviously you need to be aware that this is a challenging course and it's going to require consistent effort on your part to succeed. Now, what I will say is, having done this is now my sixth time teaching this course or something like that. So I'm not exactly a grizzled veteran, but I've been around long enough. And basically, most of the students that get D's and F's in this course, which is certainly the grades you want to avoid, it can be traced, at least in large part, to just poor study habits, a lack of effort on their part, and that's being blunt, but that's true. So we have ways of tracking your effort, through the homework attempts and things of that sort. And the students that earn the D's and F's, they're very clearly not putting in the regular effort that they need to succeed. So it's no wonder that they don't get a grade that they're happy with. So there are other factors, of course, at play. It's not strictly about effort. Obviously, your previous background and preparation and other things go into this, but there's a lot that you can control in terms of how you approach this course, and that's going to be the key to doing well. So if we look then at some more things about the homework assignments, as I said, one of the reasons we now use tie the bonus points to homework attempts is because there is a correlation between homework attempts and final grades. The students that do more homework attempts get higher final grades on average. So if we look at, I think this was also from last year or 2 years ago, I forget when I tracked this, but I took the top 15 students in my class in terms of homework attempts. So they all did between, they missed no more than 3 homework attempts the whole semester. They did, there's 52 maximum for the 13 weeks, and they all did between like 49 and 52, so basically all of them. And those students, I think about like 75% of them got A's or B's. So again, the students that are putting in the maximum effort are getting good grades. This is not one of those hopeless courses where you think if you work your hardest, it's not going to pay off. It does pay off to a different extent for everybody, but still, in general and on average, if you put in the maximum effort, you're going to be okay with your grade at the end. Now, the key point though is that doing the homework is not enough. You have to actually learn from it. And another thing that's good to keep in mind with these homework assignments, and I'm going to give you guys reminders about this all throughout the semester. So, I'm going to sound like a broken record at the end, but I think it's important to keep after these sort of principles and approaches here. Basically, we give you 48 homework problems every week, as I said, if you do all 4 attempts. And your goal at the end of the week, by the time you finish those, is to know how to do all 48 of those questions from start to finish without any resources to help you. So basically just you, your calculator, and your periodic table, what you'd have on an exam. If you can do all those questions. And you want to make sure you do that every week. Don't wait until the exam is 2 days away to start learning how to do the questions you had trouble with. So, a lot of you guys probably have backgrounds in, you probably played sports before, were in performing groups or things of that sort before. So what you kind of want to think about in this course is basically treat it like every week you have an exam, a competition, a performance, whatever you want to think about, as at the end of the week. So don't wait until the exam comes around every 4 weeks or so, but every single week, make sure you're learning everything and treat it like you have an exam every week that you have to prepare for. So if you're able to stay up with the material on that level, that does 2 things for you. First of all, when the exams do come around, you don't have to cram. You don't have to spend hours upon hours learning stuff that you still don't understand from a few weeks ago. The other thing is that, as is true in this course and is true in most science courses that you'll take, everything builds on itself. So if you slack off 1 week and don't learn the stuff very well, then the next week you're going to be even more lost because the stuff that we teach you the next week depends on how well you know the previous week's stuff. So you really have to do every single week, make sure that you know how to do all the homework questions, get help from me, get help from a tutor, whatever it takes to make sure that you're up to date on everything and not waiting until the last minute to try to cram it all in. All right, so to sort of put a little bit of a logo on this and a little bit of a slogan, if you will. So what I want to call this semester is the 1 hour per day guarantees. So basically what I'm saying to you guys now, and I 100% believe this is not just marketing, this is my true belief. If you spend 1 hour per day outside of class doing something related to Chem 1331, so studying, reviewing, practice problems, whatever the case, I'll give you examples on the next slide of how that can work. If you do that 1 hour per day, every single day, then you will pass the course. And by pass, I mean get at least a C or higher. Now, obviously, some of you have higher goals in getting a C, but you'll at least avoid the dreaded DFW territory that we want to keep everybody out of, because that's what really stalls your degree progress. All right, so if you do that 1 hour per day, then very certain you're going to be happy with your final grade, and you're going to do okay in this course. Now that has to come, that has to be something that you keep up with, though. And this, I don't think that's an unreasonable expectation either. So, you guys maybe think I'm too old to give relevant advice anymore, but when I was in college, the sort of rule of thumb was that for every hour inside of class, you should expect to spend 2 to 3 hours outside of class, studying, reviewing, and so on. So 1 hour per day in this course is about 7 hours per week. This is a 3-hour course, and that basically falls then right into that range. So, and the other thing you want to do is spend the early part of the semester getting in this habit. A lot of times people slack off at the beginning because, the first exam's not until 5 weeks later, and the material, it doesn't seem that hard, I'll be fine. And they don't get into this regular habit of studying every day at the beginning of the course, and then it's just too late once they do try to start. So it takes the average person about 21 days to build a new habit. So you really need to spend the first 3 weeks of this course getting into the habit of spending some amount of time every day, like I said, about an hour a day on something related to chemistry. And so that's something you're going to want to do early on. So once you get in the habit, it's going to get to the point where you feel like your day is not complete unless you've had your daily fix of chemistry. So you really have to get into that consistent habit of doing that, and it'll become second nature. So I want to try to emphasize this all semester, and to do that every single Wednesday. So we have, what are the things we do now, like Man Crush Monday and Throwback Thursday and what Flashback Friday and what other. Well, anyway, in this class we're going to have Work Habit Wednesday. So every Wednesday I'm going to give you some reminder of varying passive aggressiveness about the things that you need to do to make sure that you're preparing well for this course. And again, it's an every single day thing. It's not something that you do once every 3 weeks when you have an exam. So I'm going to try to keep up with this with you guys. And another key though is to remember that not all effort is created equally. So part of your challenge and part of the challenge of being a college student in general is to figure out what's the best use of that time. So it's not that you can just do anything and you're going to magically learn what you need to do, but you have to figure out for yourself, and with my help if you need it, what kind of things do you need to do on a weekly basis to make sure that you're prepared for this course. And like I said, things like, here's an example of things you can do. The 4 homework attempts, I would say, is a must for everybody. That's a good way to spend 2 to 3 hours per week. Each homework attempt is about 30 to 45 minutes, depending on how long it takes you to do that one. And if you do that, that's going to be 2 to 3 hours per week, and that's, I think, a very good first step for all of you to follow. And then I also encourage you to go back through the lecture notes and or the lecture videos for an hour or so per week. So I'll give you a lot of sample problems in lecture notes, and if you can make sure you do those, that's extra practice for you that you're not going to get in the homework. And then I encourage you, as I said, to visit me during office hours, or there's a lot of on-campus tutoring resources that are completely free and available to you that many students find useful, and that's a good way to get help on topics that even if you've gone through the lecture a couple times, even if you've done the homework assignment, you still feel like you don't follow, again, get those addressed right away. We're going to have some more information next week about one of the on-campus tutoring resources that's pretty valuable, so you'll get reminders about that and what those are available to you. It's also good to go through previous homework problems. So even after you submit the homework attempt, you can access the results in Blackboard, and I encourage you to go through it as many times as possible to feel like that 100% how to do that question from start to finish, no resources available. So repetition is really the key here. And like I said, getting help from me or from a tutor is also key when there are problems that you still get stuck on. The textbook, some students have varying opinions on how valuable the textbook is, and that's up to you to decide how valuable you think it is. But if you spend an hour or so a week reading the textbook, that gives you some additional background on the topics, additional practice problems to work for, and I would say overall it is a helpful resource. And then, like I said, we have the video resources, which I don't want you to rely on too much necessarily, but it's certainly helpful to go back through some of the challenging topics. So all these things that I mentioned, which I've already talked about before this, if you add all those up for the time that I expect you to spend on it, there's your 79 hours per week. That's your 1 hour per day guaranteed, and you're all good to go. So you need to find what works for you, but it's got to be consistent effort, and I'm going to harp on this throughout the semester. All right, so if there are any questions on the syllabus or any questions about how to do well in this course, I'm happy to address those with you anytime via email or in my office, whatever works for you. But now what we're going to do is we're going to jump right into the course material, starting with Chapter 1. So what we're going to start with today is introducing some of the very earliest chemistry concepts that evolved. And this is interesting from a sort of historical standpoint, but also sort of helps set us up for what we're getting into with the early parts of this course. So this course, if you paid attention to the title of the textbook, we use a textbook that's called an Atoms First Approach. And so what that means is we're going to do sort of atomic theory and atomic structure first, which is not always the case in Chemistry 1. So it's a little bit of an inverted order of things to some extent, but that's what we're starting with. And to get into that, we want to understand then what were some of the early chemistry concepts, some of the early chemistry experiments that really set us in the direction of understanding how atoms and molecules work in a chemistry sense. So to understand that, first we need to talk a little bit about the scientific method. So this is used in all branches of science, not chemistry, and it's especially important in the lab portion of this course. But what we want to understand is that all these things that we're teaching in this course today, and especially the stuff we're covering today, came about because of application of the scientific method. So a scientific method starts with an observation. This is something that you sense or measure. And there are two major types of observations. There's qualitative and quantitative. So qualitative is something that you don't measure. It's sort of a relative observation, or something that you perceive or sense but don't make a specific measurement on. And then a quantitative observation is one that you measure and which has a number associated with it. So as an example of a qualitative observation, if you said, the sky is blue, or Professor Teets has big hair, or something like that, that would be a qualitative observation. Quantitative is one that has a number and a unit associated with it. So the review chapter talks all about units, as we said. So any quantitative observation must include a unit. So it would be something like, I am 5 feet 9 inches tall, or this weighs 25 grams, or something like that. So it has a number and a unit associated with it, and it has to be measured. So those are the two types of observations you make. And then the way the scientific method starts is that you have some observations that you've made, and from that you develop a hypothesis, which is a possible explanation for these observations. Some people call a hypothesis a guess. That's maybe not quite accurate, because it is based on some information. It's based on observations, not just pulled out of thin air. But it's usually based on limited or flawed information. So the hypothesis is very rarely exactly correct. Limited or flawed information. All right, so it's usually based on limited or flawed information. And then you'll make that hypothesis, and then to figure out if your hypothesis is correct or whether you need to refine it or change it altogether, that's where you have to design a series of experiments to test this hypothesis. And this is where the whole point of the experiment is really just to collect more observations, but you're going to carefully control everything to be able to test the hypothesis and only make observations that directly relate to that hypothesis, ideally. And this whole process then just cycles over and over again. So the experiment leads to more observations that you make, and then you're going to use those expanded set of observations to refine your hypothesis and keep going around and around until you're satisfied that your hypothesis is fully consistent with all the observations that you've made. So that's kind of how the scientific method works. So as maybe a dumb but hopefully a little bit helpful example of this, so imagine that. So let's say let's try to do a chemistry one here. So let's say your observation was that, water exists as a liquid, as we know, at least at normal temperatures. We've had a lot of rain today, so you guys know that. So that's one observation. And the other observation is, but then oxygen exists as a gas. So there's our observation. Water's a liquid, oxygen is a gas. And then let's say having not taken a chemistry course yet, you want to come up with a hypothesis with an explanation for that. So maybe you'll say, so I think what's happening is that in water we have half the molecules are positively charged, half the molecules are negatively charged, and then they stick together. But in oxygen, all the molecules are positively charged, and so they fly apart. So that's your hypothesis. Now, if you learn anything in this course, you'll learn very quickly that that's wrong, but that's your hypothesis, is based on the information you have. And then you go about and you start testing that. So you do some experiments. You say, what happens if I, take my oxygen and I cool it down to really low temperatures? It becomes a liquid. So it's not, it's not that they can't all be positively charged, because even if you cool it down, they would still repel each other. And you do some other experiments. If I heat up the liquid, it becomes a gas. So that means, maybe that explanation wasn't correct, that you have these oppositely charged things holding each other together. So you basically do these observations and experiments, and then you figure out that your hypothesis was wrong, and you keep refining that hypothesis over and over again. Is there a question in the back? Sorry.
Yeah, sorry. But what would you say is the fundamental difference between a theory and a hypothesis?
Well, we're going to get to that here in a second when I define what a theory is. So they're actually very related to each other. So when you do the scientific method and you go through this cycle over and over and over again, two things come out of the scientific method. So the first one is a law. And this is what happens. So a law is basically an observation or a mathematical equation that we believe to be true 100% of the time. So it's something that is repeatable over and over again. We'll see it, we're going to learn about some laws today. But basically, it's an observation either with or without a mathematical equation associated with it that is something that we 100% know is true. And then what a theory is, and is very closely related to the hypothesis, is a theory is an explanation for why that happens. So the law is what happens, the theory is why it happens. And basically, a theory is, in some sense, no different than a hypothesis, but it's been validated experimentally. So a theory is a hypothesis that we believe to be true because it has been subjected to a rigorous scientific method as many times as necessary to come up with that. So theory and hypothesis are very closely related to each other, but the theory is the explanation for why the law, whatever happens, happens. And in doing that, we have sort of an observation and an explanation that are fully consistent with all the experiments we've ever done. Now, getting into more details about chemistry. So in chemistry, we apply the scientific method in all areas of science. Physics, biology, all those different sciences that we don't like as much as chemistry, they do use the scientific method. But in chemistry, what we're applying the scientific method to is the study of matter. So that's kind of what distinguishes chemistry. It's the study of matter. And we're going to learn about a few different classifications of matter, which I want to briefly summarize here, though it's not terribly important for the beginning of the course, but just to kind of contextualize where we're going to some extent. So there are two major classifications of matter. There's mixtures, and then there's what are called pure substances. Most of what we'll deal with, especially in the early part of the course, is pure substances. So pure substances are materials, chemical materials that have constant composition. And we're going to talk in more detail about what composition means as we go in these earliest chapters. But basically they have constant composition, and then a mixture is something that has variable composition. And a mixture is basically two or more of these pure substances combined with each other in a physical way. So it's two or more separate substances that are just sort of blended together, but not anything new fundamentally. All right, but we're not talking about as much with mixtures in this course. But with pure substances, there are then two major types of pure substances. And understanding the distinction between these is a very important concept for the early stuff we're going to learn in chemistry. So the two types of pure substances are elements and compounds. All right. So an element is what we call a fundamental substance. It cannot be broken down into any simpler substance. All right, and we're going to get sort of the more atomic level definition of what an element is a little bit later, but it's a substance that can't be broken down any further. It's sort of the fundamental building block of all other substances. And there are roughly 90 or so, maybe a little bit more than that, but around 90 or so elements that occur naturally on Earth. There's another almost 30 now that have been discovered by artificial means, but these are basically the fundamental substances that you cannot break them down any further without changing them into a different element, but you can't use chemical means to break them down. And then compounds are combinations of elements that have been chemically combined in different ratios. And so basically the essence of chemistry is sort of converting elements into compounds by mixing them together and making new chemical interactions. So a lot of details that we have to leave out for now, but basically elements are the simplest substances that can't be broken down. Compounds are combinations of elements, and then if you break down a compound, you will eventually get to the elements that make it up. All right, so that's what a compound is. It's a combination of elements. But not a mixture, because in this case, the elements are actually combined chemically, and we're going to learn what that means in the first part of this course. And then within mixtures, which we're not going to deal a lot with this in this course, but just to be complete, there are two classifications of mixtures as well. There's homogeneous and heterogeneous. So homogeneous is what we call a single phase mixture. It basically means that you have two or more things mixed together, but you can't easily distinguish the two components. So if you dissolve salt in water, it looks like just regular clear water, but it's still a mixture of two things, salt and water. You just can't easily tell that it's a mixture of two things. But then a heterogeneous is something that has visibly distinguishable parts. So a heterogeneous mixture, you can tell just by looking at it that it's a mixture where you can easily see the two or more different parts that make it up. So Sand is a heterogeneous mixture. If you look really close at grains of sand, you'll see a few different colors in there because it's a few different minerals that are all mixed together. Milk, in some sense, is a heterogeneous mixture because you can't see through it because you have the white cloudy stuff is the different fats and proteins in milk that aren't completely dissolved. Or if you mix oil and water, that gives you a heterogeneous mixture where you have visibly distinguishable parts. So you can tell in a heterogeneous mixture that you have two or more things mixed together. And then it's also important, and we're going to, again, this is stuff that we're going to just touch on very broadly at the beginning, but it's also important to think about the classification of matter in terms of the particles that make up that type of matter. So we're going to get into a lot of this in the beginning of the course, but basically in chemistry we have two fundamental particles we're going to talk about, atoms and molecules. So atoms are the building blocks of elements. So if you have an element, it's going to be made up of one type of atom. So we're showing them here all the same color. So you can have elements where it's just single atoms floating around in the sample, or there are elements where two or more atoms of the same type are sort of bonded to each other. But the key thing is that for any element, you only have one type of atom, either all red or all blue, as I'm showing here. And then when you make a compound, you're going to take two or more different kinds of atoms, two or more, atoms from two or more different elements, and you're going to bond them to each other by chemical bonds. And so like compounds would have, for example, one blue and one pink, or you can have different ratios, in this case one pink with four small black ones around it. So we're not getting into the details of what these could represent, but basically a compound is where you take two or more elements and you combine them to make what are called molecules. So element is made up of atoms, compounds are typically made up of molecules, and then mixtures are going to be two or more of these substances mixed together. So this mixture here would be a mixture of elements because it has two types of atoms, red and blue, but they're not really attached or bonded to each other. They're just sort of blended with each other, physically speaking. This over here is a mixture of compounds, because what we took is each of these two types of molecules here, the one that has one blue and one pink, the one that has one pink and four black, and we blended them together. And there's no new chemical attachments, but the two substances, the two compounds, are physically blended together. So this gives you sort of a microscopic view of how this looks, and that's kind of what we're going to work towards at the beginning of this course, is taking some of these larger scale physical observations and physical classifications of substances and then breaking that down to look at what does that mean for us when we go at the microscopic level and look at the individual atoms and molecules that make up those substances. So that's going to be a key connection that we have to make really throughout this course, but especially at the beginning when we talk about atomic and molecular structure in more detail. So there's a lot of details that I have to leave out for now, but that's kind of be what we're sort of working towards in this course. What I want to get into now then is a little bit about early chemical history and some of the key observations and then laws that came about from those observations that sort of helped really bring about the field of chemistry as a science. Now, a lot of this goes back to the ancient Greeks, so thousands of years ago. And they were really the first to be sort of intrigued by studying substances and chemical changes and things very, very primitive by today's standards, but they were they were trying at least. They weren't particularly successful at really learning anything that's true or useful, but they put a lot of effort into trying to explain chemical changes. So they studied chemical changes and made some observations about them. And what they led to was a proposal of 4 fundamental substances. And if any of you are Captain Planet fans, you'll know what these are. So, earth, fire, they didn't call it wind, they called it air, and then water. They did not discover heart as the 5th fundamental substance. Anybody here know Captain Planet, or am I just that old? There was a popular cartoon when I was a kid, but not when you guys were kids, obviously. All right. Anyway, so the ancient Greeks proposed 4 fundamental substances. So this is, clearly not how I think about chemistry today, but it was really the first attempt to classify things and to systematize things. So they certainly deserve a lot of credit. And the one thing they did that's pretty remarkable, considering how long ago it was and considering they had no way of actually observing these things, was they were the first to propose atoms as fundamental particles. In fact, the word atom comes from a Greek word atomos, which I don't remember what it means in Greek, but anyway, it is a Greek word, and they were the first ones to actually propose something like this, where you have these really tiny fundamental building blocks that make up all substances. Now, they didn't have any information about what those would look like, and obviously they thought that earth, fire, air, and water were fundamental substances, which is not true, but they also proposed the idea of atoms, which is pretty remarkable considering how long ago it was. A large part of chemical history during, let's say, the sort of the AD period, up until like the Middle Ages, basically, so was called alchemy. So you had the alchemists, as they're called, and they studied alchemy, which is what we would call a pseudoscience. So kind of in the same category. I don't want to offend anybody, but kind of in the same category as like essential oils and stuff like that, where it's not based entirely on false statements. It's not completely garbage, but at the same time, it doesn't also tell you the whole story, right? It's leaving out some important things and doesn't really follow a very careful scientific method. So they didn't really follow the scientific method, but again, they still made a lot of observations and studies about chemical compounds and chemical substances. And this period of chemical history spanned a long time, about 2,000 years. So it was a long period of history. And even though we didn't really systematize the science of chemistry during that time, during those 2,000 years, we still learned a lot of important things. But their key goal, and really what they based a lot of their efforts on, was they were trying to turn base metals like lead into gold. And they thought that this could be done, and that was sort of their all-encompassing approach, their all-encompassing pursuit, was to change lead into gold. All right, because as was the case back then, gold was still, the material that made you rich and famous, and so the more gold you had, the better off you were. And so they thought, well, if we can do chemistry, or alchemy as it was called now, and we can change lead into gold. Now it turns out that's not really possible to do. So they were chasing, a goal that had no chance of actually happening. But they still made a lot of important observations along the way about chemical substances, and a lot of, as this painting shows, a lot of the apparatuses that they use to do their alchemy are still apparatuses that are very much in use today. So they made a lot of important developments, just didn't really teach us a lot of anything real about chemistry. Where chemistry really started was with Robert Boyle. He's what we consider the first chemist. And what he did was he made quantitative measurements on gases. So we're going to talk about what's called Boyle's law much later on in the course when we talk about gases. But he actually was really the first person to do very systematic studies on chemical compounds, and also to really use the scientific method towards understanding chemistry, understanding matter. And he did it on gases, and he did purely physical measurements. So he wasn't really changing one substance into another as he was doing this. He was just taking a single substance and measuring things like its temperature, its pressure, its volume, all the stuff we're going to learn about later. But it was still a very important birth to the field of chemistry. But he also proposed the concept of elements, sort of more in the modern sense of, fundamental substances that can't be broken down any further. Not earth, fire, air, wind, and whatever, but real chemical substances that are what we call elements, and that are sort of the fundamental materials that build up all the rest of chemistry. And then another person who's very important in early chemical history is Joseph Priestley. He discovered oxygen, and he was really one of the first, or the first people to do very detailed studies of chemical reactions. So as I said, Boyle was just making physical measurements on the properties of gases, but he actually studied chemical reactions, also primarily involving gases, as it turns out. But in the course of doing this, he discovered oxygen, discovered that there is some chemical substance in the air that we can't see or can't smell or can't taste, but it's still this important substance, oxygen, that plays a role in a lot of chemical reactions. And then he started really understanding how we can turn one substance into another, and how to sort of systematically study that in very good detail. So this is kind of the early chemical history that gets us into what we're going to start out with in this course. And what this course starts out with are the three mass laws. And these three mass laws will lead, as we'll see, to the development of the atomic theory. It's really the development of the idea that all substances are made up of atoms. And the first mass law that we want to talk about, these are not necessarily in chronological order, but the first one that comes up is called the law of mass conservation. This is attributed to Antoine Lavoisier, who, as you might guess, is French. Antoine Lavoisier. So this is the law of the conservation of mass. So what we have here to sort of introduce this is a video that will show you how this works. So in this don't change the total mass at all, okay? So matter is neither created nor destroyed. So there's sort of two different ways of stating this law of mass conservation. In a chemical reaction, the mass of what you start with, so the things that you're mixing together in the chemical reaction, in chemical terms, we call these the reactants, which we will systematize a lot more later on, is equal to the mass of what forms. All right, so anytime you convert two or more substances into something else by doing a chemical reaction, the mass before and the mass after are the same. Now, maybe this sounds trivial, but it's actually kind of hard to figure out because so many of the early reactions that people studied in chemistry were basically just setting things on fire. One of the most enjoyable and easy reactions for us to do. And when you set something on fire, it, as we'll learn later on, it burns with air with oxygen from the air. It forms products that sometimes are gases and then float away. So if you're trying to measure the conservation of mass in a combustion reaction when you burn something, that's very hard to do because you have to be able to basically enclose everything and control that all the gas that is used to burn it is accounted for, and all the gas that escapes from the reaction is also accounted for. But through careful study, eventually they figured out that whenever you do a chemical reaction, you don't change the mass before and after, and that another way of saying this then is that matter is neither created nor destroyed in a chemical reaction. All right. Now, if you stick with us all the way until the end of Chem 1332, which is not even the end of this semester, but the end of next semester, if you take the full sequence, you will start learning about situations where the law of conservation of mass doesn't quite hold whenever you're doing what's called nuclear chemistry. But for our purposes, this is 100% true, and matter is neither created nor destroyed in a chemical reaction. Now, the second mass law that we want to cover is called the law of definite composition. And this came about by careful studies of chemical compounds, okay? And it was formulated by Joseph Proust, who's credited with it. Maybe that's Proust, I don't know the proper pronunciation of his name, but we don't want you to know too many of these names, but a few of them are important to have in the back of your mind. And definite composition basically deals with the composition of a single compound. And so if you have a given compound of any type, again, a pure substance, a pure compound by itself, not a mixture, but a pure substance, it's going to always contain the same proportion of elements by mass, regardless of where you get that compound from. All right, so that basically means every chemical compound has a fixed ratio of element masses that make up that compound. And what we mean by regardless of sources, it doesn't matter where that compound comes from, it's always going to be the same anywhere. So the example we're going to give is carbon dioxide. So we've all heard of carbon dioxide. It's the gas that we exhale when we breathe out. It's also formed when you burn something. And if you look at carbon dioxide, whether it's the carbon dioxide that you breathe out, carbon dioxide that burns, carbon dioxide that's released from the ocean when it when it warms up, any source of carbon dioxide you can think of is going to have the same mass ratio of carbon and oxygen. It doesn't matter where it comes from. And so as an example, if we have 44 grams of carbon dioxide, where these numbers come from will become obvious much later in the course, but for now, if we have 44 grams of carbon dioxide, it will always contain 12 grams of carbon and 32 grams of oxygen. Now you'll also notice that the law of conservation of mass sort of plays into this, because if we have a compound that's made up of carbon and oxygen, 32 grams of oxygen, 12 grams of carbon, total is 44. So whenever you combine elements to make a compound, the sum of the element masses also has to equal the total mass of the compound. That also follows from the law of conservation of mass. Now the way that we express these usually, though, is because this ratio is going to be true no matter how much carbon dioxide we have. So the relative amounts of carbon and oxygen will be the same whether you have one little tiny bit of CO2 or a whole room full, as we have now, having been in here metabolizing for the last hour or so. So anyway, what we express these in as is a mass percent, which allows us to sort of normalize it to a consistent amount. So typically, for each compound, we're going to define the mass percent of each element in the compound. So in carbon dioxide, the mass percent, let's just start with the general definition first. The mass percent in general is going to be the mass of the element divided by the mass of the compound multiplied by 100. So for every compound, for each element in that compound, you can define a mass percent, which is the mass of the element in that compound divided by the total mass of the compound multiplied by 100 to make it into a percentage. This is also sort of what's referred to as the mass fraction. So this ratio here, that's the first part, is mass fraction, and then you multiply the mass fraction by 100 to get it to a percent, okay? So that's kind of the terminology associated with this mass percent and mass fraction, related but slightly different. And this is how you calculate it. So for carbon dioxide, we can calculate a mass percent for each element. So we can do it for oxygen, which would be taking the amount of oxygen in the compound, 32 grams, divided by the amount of carbon dioxide total, the amount of compound that we have, which is 44, and then multiply by 100. And so we get 73% for oxygen. And if we do the same thing for carbon, we saw that we had 12 grams of carbon in the compound. The total mass of the compound is 44 grams still, and we multiply that by 100, we get 27%. And as they should, these two numbers add up to be 100%. So anytime you calculate all of the mass percents for a specific compound, the sum will have to be equal to 100 if you did your math correctly. And the point of this is that no matter how much carbon dioxide we were measuring, the percentage of oxygen would always be 73%, the percentage of carbon would always be 27%. Those numbers don't change no matter how much of the compound you have. And that's why they're a useful quantity for us to quote. Now, we're not going to end up using mass percents for all that long, but this was sort of one of the early ways that people in chemistry sort of classified substances, was based on the mass percent of each element. So here's some example problems just to close out today. So we have fool's gold, which is called pyrite, or is the formal name. You may have seen this before. It looks a lot like gold, but it's not. It's actually not valuable at all. It looks nice. And anyway, if we have fool's gold, if we have a 50-gram sample of this pyrite, it contains 26.7 grams of sulfur. What is the mass percent of iron in pyrite? Now, the way that I like to set up problems, and this is what I'm going to use throughout this course, is go to the end of the question first. So we're going to, in homework assignments and tests, a lot of times we're going to have these word problems. This one's not particularly long, but we're going to have these long problems where we give you a lot of information, sometimes 2 or more sentences you have to sort of sort through. The best way to start these problems is go to the very last sentence, because that's typically going to have what we're asking you. So what we're asking you for is the mass percent of iron in pyrite. And so what's helpful to then write out before we even start going through the rest of the information is, okay, what information do we need to figure out the mass percent of iron and pyrite? Well, based on the definition of mass percent that I just gave you, what we need is the mass of iron. We also need the mass of pyrite. So remember, it's element divided by a compound, and then we multiply that ratio by 100. And so if we have these two numbers, the mass of iron in the sample, the mass of pyrite that we have in total, those two numbers together will give us the mass percent of iron once they're divided and multiplied by 100. So then we look at the rest of the problem to figure out how we get the rest of this information that we need. So the one that's given to us is the mass of pyrite. So in many cases, a lot of the information that we need to solve the problem will be directly stated for us. So the mass of pyrite, we have a 50-gram sample of pyrite, so there's our mass. So that number is given to us directly. We don't have to do any intermediate steps to figure it out. But the one that we don't have directly is the mass of iron. So if we look at the rest of the information of the problem told us how much sulfur we have, but it didn't tell us how much iron we had. But remember, from the law of conservation of mass, if we have a compound that's made up of two elements, iron and sulfur, the sum of those two masses has to equal the total mass. So that 50 grams of pyrite that we have, that 50 grams is going to be the sum of the masses of each element, iron plus sulfur. And so then if we solve for the mass of iron, it's 50 grams, which is the mass of the compound, pyrite, minus the mass of sulfur, which is 26.7 grams. We're just doing a little bit of algebra here. And the rest of that mass would have to be the iron in the sample, 23.3 grams, all right? There's only two elements, so the sum of the two has to equal the mass of the compound. And so now we have all the information we need to solve what we're looking for. So we take the mass of iron that we just found, 23.3 grams. We divide it by the mass of the compound, which is pyrite, 50 grams, multiplied by 100, and we get 46.6%. Now, the other way you could have done this was you could have found the mass percent of sulfur and then subtracted that from 100. That should also give you the same number. So many times there's more than one way to do a problem, but I do think it's very helpful at the beginning of any problem to go to the end, figure out what we're asking, figure out what information we need, because sometimes you don't need all the information or sometimes some of it is right there for you. All right. All right, and then the very last one I'll do is a related topic, so same substance, pyrite. But now what we want to know is how many grams of sulfur are in a 1.235 gram sample of pyrite. Okay, so we know that 50 grams of pyrite contains 26.7 grams of sulfur, but if we had a smaller sample, 1.235 grams, how much sulfur would be in there? Okay, and the way that we're going to set this up is using the mass ratio of sulfur to pyrite as a conversion factor. So the review chapter has a lot about conversion factors. I went through that in the review lecture that I posted if you want to check it out. But basically, again, we start with what we're looking for. We're looking for how many grams of sulfur are in the sample. The given information is that we have a 1.235, or our starting point is a 1.235 gram sample of pyrite. And then we're going to use the rest of the given information as a ratio. So what we want is we want grams of pyrite to cancel out, and we want to convert that into grams of sulfur. And the mass ratio that we have, or alternatively the mass percent if we calculated it, gives us that information directly. So 26.7 grams of sulfur per 50 grams of pyrite is the numbers that we were given in the text. We could convert those to a percent, or we can leave them exactly as they're given to us. And now what we see is that grams of pyrite cancels out, and we get into grams of sulfur as our units. This is what's called dimensional analysis, converting one unit into another, grams of pyrite into grams of sulfur, using, in this case, the mass ratio, which comes from the law of definite composition. And so numerically what this comes out to is 0.659 grams of sulfur, which matches up with choice A. All right, so the key concept that I introduced in this problem, which we're going to see on a lot of the homework questions in the first part of this course, is that the mass ratios can be used as conversion factors. All right, so if we know relationships between the mass of one element and the mass of another element, and then the mass of a compound that's made up of elements A and B, if we know these relationships, we can use those relationships as conversion factors to convert between any of these quantities here in any direction, okay? So we'll probably see some more examples of that in the next lecture, but at the very least, you'll see it on the first homework assignment. So that takes me to the end of our first lecture today. I'll see you guys on Wednesday, where we'll continue on with the third Mass law and start introducing atomic theory.